for the function f of x equals x squared minus 2x minus 3 over x squared minus 1, I want you to find the domain, any holes, and any vertical asymptote that exists for this function. So the first thing I want you to identify is the domain. Before reducing, we're going to set the denominator equal to 0 or not equal to 0 and find out what the excluded values are and list the domain in interval notation. So x squared minus 1, it cannot be equal to 0 because it's a denominator. So x cannot be 1 or negative 1. My domain in interval notation would be negative infinity to negative 1, union negative 1 to 1, union 1 to infinity. But notice that we have two excluded domain values. Of these two excluded domain values, we may have holes or may have vertical asymptotes at these 2 points. I need to figure out which one's which, or if I have any. To find a hole, we need to factor and reduce. If a factor cancels out or divides out, then that's going to be a hole. If, after we factor and reduce, if we have remaining terms in the denominator, then we set those equal to 0 and solve, and that will be our vertical asymptote. So the difference between a hole and a vertical asymptote, when you're looking for them, is holes are factors that divide out, and vertical asymptote comes from factors that don't divide out. So let's go back to the original function and factor the numerator and factor the denominator. I'm getting x minus 3 times x plus 1 and x plus 1 times x minus 1. Is there any term that divides out? Well, there is. X plus 1 and x plus 1 divides out. So because there's a factor that divides out, we have a hole. And the hole occurs when x plus 1, the factor that divides out, equals 0. So that occurs when x is equal to negative 1. Notice that's one of our excluded domain values. So my hole occurs at negative 1 comma some value. So how am I going to find the y value of the hole at negative 1? Well, to find the y value, I'm going to plug it back into my function. But some of you might be thinking, well, you can't plug it back into the function because it's not defined there. That's what we were all talking about. It's not defined in our domain. It cancels each other out. How are we going to find this? Well, what we're going to do is we're going to use the reduced function like we talked about in the instructions. So when I use the reduced function and evaluate the reduced function at negative 1, this is the point at which it would be if it wasn't a hole. So I have negative 4 over negative 2 or 2. So I have a hole at negative 1 comma 2. On my vertical asymptote, I factor and reduce, and I use the remaining reduced function. If my remaining term is in the denominator, and I do have terms in the denominator, I set that denominator equal to 0, and that is my vertical asymptote. My vertical asymptote is x equals 1, which happens to be a vertical line. Always x equals is always a vertical line. Notice that the vertical asymptote at x equals 1 is the other part of my excluded domain. So the excluded domain values will tell you if you either have a hole or vertical asymptote, so they're all very related. And a lot of students have a hard time figuring out which one is which, so that's why I put them all three here together. The domain is found by setting the denominator equal to 0 before reducing. The holes are found by setting the denominator equal to 0 if it divides out. And the vertical asymptote is found after reducing if it doesn't factor out, if you still have terms in the denominator. And that's the difference between those three. Let's do 3 more examples here. I'm not going to have you find the domain this time. I'm just going to have you find the vertical asymptote and the holes. So I'm going to factor the numerator and factor the denominator of my first example. If a factor divides out, that tells me I have a whole. If no factors divide out, then I don't have any wholes. Well, in this case, x plus 1 does divide out, so that tells me I have a whole at -1 comma some value. To find that other value, I look at the reduced function. The reduced function is f of x equals x minus 1 over x. And if I evaluate at f of -1, I'm finding I have -1 minus 1 over -1, or I'm getting a value at 2. So I have a whole at -1 comma 2. Now I would like to find any vertical asymptotes. I should have asymptote right here. To find the vertical asymptote, I look at the reduced function. And the reduced function is f of x equals x minus 1 over x. I set the denominator equal to 0 and solve. Well, that was an easy one because it was basically already solved for us. Alright, let's try this again. For the next function, I factor the numerator, I factor the denominator. Doesn't look like the numerator factors at all, but I believe the denominator does here, and use any factoring methods that you're comfortable with. I have 3x, looks like plus 2, and x minus 1. That gives me a minus 3 plus 2, and that gives me the -1 middle term. Does anything divide out? Well, no, there's no factor in the numerator and the denominator that divides out. So I have no wholes. Looking at the reduced function, which in this case the reduced function was the original function because there's no factors that divide it out. To find the vertical asymptotes, and again there may be more than one, I set the denominator equal to 0 and solve. That gives me a vertical asymptote at x equals 1. I also have a vertical asymptote at x equals -2/3. I found those by setting the denominators equal to 0 and solve. On our last one, f of x equals 4x squared plus 3x over x minus 5. I would like to factor to see if I can divide out. Factor out x in the numerator and I get 4x plus 3. In the denominator, there's no terms to be factored out. If I have a factor in the numerator and denominator that divide out, then I have a whole. Well, there's no factors that divide out, so I have no wholes here. Using my reduced function, which again in this case is the same function, my vertical asymptotes are going to be setting the denominator equal to 0, and I'm left with x equals 5. Notice it's always x equals because that's a vertical line is always written as x equals some number. So when you solve it, you leave the x there. Please don't just write 5. That's not a vertical line, that's a number. So that concludes our examples on vertical asymptotes and wholes. Next, we'd like to talk about a horizontal asymptote.
Horizontal asymptotes and crossing the horizontal asymptote. To find the horizontal asymptote, we are going to compare the degree of the numerator with the degree of the denominator, which will produce 3 cases. So let's say we have f of x equals a polynomial on the top over a polynomial on the bottom. I know this is really complex looking. We're looking at a sub m x to the m plus a sub m minus 1 times x to the m minus 1 plus a whole bunch of other things over b sub n x to the n plus b sub n minus 1 to the times x to the n minus 1 plus a whole bunch of other things. But I just want you to understand we're really just focusing on the leading coefficient term in the top, the leading coefficient and its term in the bottom. Okay? For example, if we had something like 3x squared plus a whole bunch of other stuff in the top over 4x to the 5th, plus a whole bunch of other stuff in the bottom. The a sub m is just the 3. The m is the exponent up here, 2. The b sub n is the 4, and the n exponent is the 5. Okay, so I know it's a really complicated notation, but we're just looking at those values. And we are trying to use the degrees, and we're going to compare them to find the horizontal asymptote. As a reminder, an asymptote is a line that the graph gets really, really close to but doesn't touch. Here's an example over here to the side of a graph, the red line getting really, really, really close to this dotted line but never crossing it. Okay? In the horizontal asymptote case, there is a possibility that we may cross it, and we're going to come to that in a little bit. But for now, we're just going to try to find out where the horizontal asymptote is, and then after we find that, then we'll find out when and if it possibly crosses the horizontal asymptote. Okay, so what I want you to do is I want you to compare the degree of the top with the degree of the bottom. So if the degree of the top, the numerator, is bigger, then in this case m is bigger than n, so the degree m in the top is bigger than the degree in the bottom. So let's say the degree of the numerator is bigger. In that case, you will have no horizontal asymptote at all. Okay, then you'll have another case where the top and the bottom have the same degree. For example, like x squared on the top and then x squared on the bottom. The degrees are the same. If the degrees are the same, then your horizontal asymptote will be y equals a sub m, which is the leading coefficient of the top, over b sub n, which is the leading coefficient of the bottom. And then our third case will be if m is less than n, or another way of saying that, the degree of the denominator is bigger. In that case, my horizontal asymptote will just be y equals 0, or in other words, the x-axis. Okay, so let's practice this. Looking at my first problem, f of x equals x squared minus 1 over x squared plus x. The degree in the top is 2. The degree in the bottom is 2. So comparing the 2 and the 2, is the top one bigger, the bottom one bigger, or are they the same? Well, in this case, they're the same. So we're looking at the middle case. So my answer will be y equals the leading coefficient, which in this case happens to be 1, over the leading coefficient of the bottom, which happens to be 1. So 1 over 1 is 1, so my horizontal asymptote is y equals 1. Now we're going to come back and use the space at the bottom for another activity, so just go ahead and leave a little space there at the bottom, okay? And let's do the next problem. The next problem, the degree of the numerator is 1. The degree of the denominator is 2. So comparing the numerator and the denominator, which one's bigger? Well, in this case, the denominator is bigger. So that's our third case where the degree of the denominator is bigger. So my horizontal asymptote will be y equals 0. On our third case, the degree of the numerator is 2, because that's the highest exponent. The degree of the denominator is 1, because there's an invisible 1 right there in the exponent. So comparing the 2 to the 1, which degree is the biggest, the top, the bottom, or the same? Well, in this case, the degree of the numerator is bigger. So therefore, there is no horizontal asymptote at all.